Introduction and Basic Concepts. This topic introduces heat transfer as a branch of engineering science that is closely related to thermodynamics, but focuses on different questions. The main concern is how energy is transferred due to temperature differences and how this process can be quantified. Many engineering systems, from power plants to electronic cooling, depend on these basic principles. The analysis is always based on energy balances and fundamental physical laws. A solid understanding of these basics is essential before moving to more advanced applications. Lesson plan: heat transfer. The course structure is arranged progressively from basic concepts to advanced applications, such as heat exchangers and radiation. The order of chapters shows that conduction must be understood before moving to convection and radiation. Each topic is connected and forms a complete framework for heat transfer analysis. By following this sequence, analytical skills develop from simple cases to more realistic systems. This structure also reflects how heat transfer problems appear in real engineering practice. Learning outcome. The learning outcomes emphasize the close relationship between thermodynamics and heat transfer as complementary disciplines. Understanding the difference between energy, heat, and their transfer mechanisms is a fundamental requirement. The ability to perform energy balances and identify conduction, convection, and radiation is strongly emphasized. Awareness of the cost associated with heat losses is also an important engineering perspective. All these goals are aimed at enabling systematic solutions to real engineering problems. Heat retention in insulated systems. Insulated systems are designed to minimize the rate of heat transfer so that the internal temperature can be maintained for a longer time. A simple example is a thermos that keeps beverages hot or cold. Thermodynamics alone cannot predict how long the cooling or heating process will take. Heat transfer analysis is required to quantify the rate of energy loss. This concept highlights the importance of thermal resistance in engineering design. Heat flow principles. Heat transfer always occurs from a region of higher temperature to a region of lower temperature. This is a natural process that continues until thermal equilibrium is reached. A daily example is hot coffee that slowly cools down in a room. The direction and rate of heat transfer depend on the temperature difference and the properties of the medium. This principle forms the basis of all subsequent heat transfer analyses. Applications of heat transfer. Heat transfer plays a crucial role in regulating the human body temperature through heat exchange with the environment. In industrial systems, it is used in heating, cooling, and refrigeration processes. Electronic devices strongly depend on effective heat dissipation to avoid overheating. Without proper control of heat transfer, system reliability and lifetime would decrease significantly. Therefore, heat transfer is always a key aspect in engineering design. Early concept of heat transfer. In the 19th century, heat was considered an invisible fluid called caloric. This caloric was believed to flow from a hot body to a cold body through the contact surface. This view helped explain the direction of heat transfer qualitatively at that time. However, the theory was later replaced by the modern understanding that heat is a form of energy transfer. This conceptual change became a major milestone in thermal science. Check your understanding number 1. This question reinforces the historical term used to describe heat in the 19th century. The correct answer is caloric, according to the old theory that treated heat as a fluid. Although this concept is no longer used, understanding it is important to see the evolution of science. This history shows how scientific understanding can change over time. From here, the transition to the modern energy-based view becomes clear. James Prescott Joule. Joule demonstrated the equivalence between mechanical energy and heat through systematic experiments. Joule's law relates heat production to electric current and resistance. Another important contribution is the Joule-Thomson effect, which enables refrigeration applications. These findings strengthen the view that heat is a form of energy, not a fluid. Joule's role is central in building the foundation of modern thermodynamics. Mathematical modeling steps. Mathematical modeling starts by identifying the important variables and relevant physical laws. Then, assumptions are made to simplify the system without losing the main characteristics of the problem. Differential equations are formulated together with boundary and initial conditions. The next step is to solve these equations using appropriate methods. The final results must always be interpreted back in the context of the real physical system. Role of modeling in engineering. Modeling is used to simplify complex real systems so they can be analyzed in a rational way. This simplification always involves a trade-off between accuracy and analytical convenience. With a model, the thermal behavior of a system can be predicted without performing expensive experiments. A simple example is modeling a potato as a homogeneous body when heating it in an oven. This approach helps engineers understand the main trends before dealing with more detailed complexities. Internal energy versus enthalpy. Internal energy represents the microscopic energy of a non-flowing fluid. For flowing fluids, enthalpy is more appropriate because it already includes the flow energy. This distinction is very important in the analysis of closed systems and control volumes. Choosing the correct energy property simplifies the energy balance equations. Therefore, the physical context of the system determines whether U or H should be used.
Check your understanding number 2. This question tests the understanding of the difference between internal energy and enthalpy. The correct answer is that enthalpy includes internal energy and the energy associated with flow. This concept is fundamental in the analysis of flowing systems. Choosing the wrong energy property can make the balance equations more complicated or even incorrect. Therefore, this understanding must be mastered from the beginning.
Understanding specific heat. Specific heat is defined as the energy required to raise the temperature of a unit mass by 1 degree. The required energy always depends on the mass, the temperature change, and the value of the specific heat. Each material has a different specific heat as a physical property. Materials with high specific heat can absorb more energy for the same temperature rise. This concept is essential in heating and cooling calculations. Specific heat variation with temperature is not truly constant and can vary with temperature. At higher temperatures, more energy is often required to raise the temperature by 1 degree. This shows that thermal properties can depend on operating conditions. For accurate analysis, this variation should be taken into account. However, in many engineering cases, using an average value is still sufficiently accurate. Properties of incompressible substances. For incompressible substances, the specific heats at constant pressure and constant volume are considered equal. This greatly simplifies energy analysis for liquids and solids. With a single specific heat value, calculations become more direct and practical. This approach is widely used in analyzing the heating of water or metals. The simplification is valid as long as pressure changes do not significantly affect thermal properties. Check your understanding number 3. This question reinforces the special property of incompressible substances. The correct answer is that the two specific heats are equal. This concept is used almost all the time in heat transfer calculations for liquids. By remembering this, many energy equations become much simpler. This is an example of how a proper physical assumption simplifies analysis. Heat transfer mechanisms. Heat transfer can occur as sensible energy or latent energy.
Sensible energy is associated with temperature change without a phase change. Latent energy is associated with phase change, such as evaporation or condensation, without temperature change. All these processes are still driven by temperature differences. Understanding this distinction is important for analyzing many thermal processes in industry. Heat flux concepts. Heat flux represents the heat transfer per unit surface area. This quantity is very useful for comparing the intensity of heat transfer in different systems. Mathematically, heat flux is obtained by dividing the total heat transfer by the area. This concept assumes that the heat transfer is uniformly distributed over the surface. With heat flux, thermal design analysis can be carried out in a more standardized way. Steady-state energy transfer. At steady-state conditions, there is no accumulation of energy within the system. The energy entering the system is always equal to the energy leaving the system. This makes the energy balance very simple and time-independent. All energy interactions, whether in the form of heat, work, or mass flow, must be balanced. This concept is the basis for analyzing many engineering devices that operate continuously. Closed system energy transfer. In a closed system, energy changes are caused only by heat and work interactions, with no mass flow. If there is no work interaction, the change in system energy is entirely due to heat transfer. In simple cases, the relation between heat, mass, specific heat, and temperature change can be used directly. This equation is widely used in the analysis of heating or cooling of solids and liquids. This approach highlights the direct link between heat transfer and changes in the thermal state of the system. Check your understanding number 4. This question emphasizes that the energy change in a system with no work interaction is caused by net heat transfer. The correct answer states that specific heat determines the amount of energy change for a given temperature change. This concept is a direct application of the energy equation for a closed system. By understanding this, many heating and cooling problems can be solved quickly. It also shows the importance of correctly identifying the type of system being analyzed. Mass flow rate in pipes. Mass flow rate depends on the fluid density, flow velocity, and the cross-sectional area of the pipe. For a circular pipe, the cross-sectional area is determined directly from the diameter. The average velocity represents the bulk motion of the fluid passing through the section. This concept is very important in the analysis of flow systems and heat exchangers. Without knowing the mass flow rate, energy transfer in flowing systems cannot be calculated. Energy transfer in control volumes. For a control volume under steady conditions, the rate of energy transfer is balanced by the change in energy of the fluid flowing through it. This energy change is usually expressed in terms of the temperature difference between the inlet and the outlet. The amount of transferred energy is strongly influenced by the mass flow rate and the specific heat of the fluid. This concept is the basis for calculations in heaters, coolers, and heat exchangers. This approach emphasizes viewing the system as a flow process. Heat transfer at outer wall usually involves 3 mechanisms at the same time. Heat flows through the wall material by conduction from the inner side to the outer side. From the outer surface, heat is released to the air by convection and also emitted by radiation. These 3 mechanisms act simultaneously and determine the total heat loss rate. The analysis of building walls and pipes always considers this combined effect. Check your understanding number 5. This question emphasizes the mechanism of heat transfer from a wall surface to the surrounding air. The correct answer is convection, since it involves interaction between a solid surface and the surrounding fluid. This concept appears frequently in the analysis of heating and cooling of surfaces. Understanding the dominant mechanism is essential for selecting the appropriate correlations. It also helps in designing effective cooling systems. Heat conduction in plane wall. Heat conduction in a plane wall occurs due to a temperature gradient between the two sides of the wall. Heat flows from the high temperature side to the low temperature side through the wall thickness. The heat transfer rate is influenced by the area, wall thickness, and material properties. The thicker the wall, the greater the resistance to heat flow. This concept is the basis of many thermal insulation calculations. Thermal conductivity and heat transfer. Thermal conductivity indicates a material's ability to conduct heat. Materials such as copper have high conductivity, allowing heat to flow rapidly. In contrast, materials with low conductivity resist heat flow. For the same geometry and temperature difference, the heat transfer rate is determined solely by the conductivity value. This is why material selection is very important in thermal design. Jean-Baptiste Joseph Fourier. Fourier developed the mathematical foundation of heat conduction through the heat diffusion equation. He also introduced Fourier's law, which is the cornerstone of conduction analysis. In addition, Fourier series and Fourier transform have wide influence in many fields of engineering. His contributions are not limited to heat transfer, but extend to applied mathematics in general. His role is fundamental in building modern heat transfer theory. Heat conduction analysis. In conduction analysis, the cross-sectional area is defined as the product of width and height perpendicular to the direction of heat flow. This area directly affects the magnitude of the heat transfer rate. The larger the area, the greater the amount of heat that can flow under the same conditions. Therefore, system geometry is always an important part of the analysis. Accuracy in defining the area strongly determines the accuracy of the final result. Check your understanding number 6. This question reinforces the definition of cross-sectional area used in conduction analysis. The correct answer is width, since the area is defined as the product of width and height. This concept seems simple, but is very important in heat transfer rate calculations. An error in defining the area will directly lead to an incorrect result. Therefore, careful attention to system geometry should never be neglected. Determining thermal conductivity. The thermal conductivity of a material can be determined experimentally under controlled heat flow conditions. By measuring the temperature difference, material thickness, and heat transfer rate, the conductivity value can be calculated. The system must be well insulated so that heat flows only through the test specimen. This approach shows that material properties can be obtained from experimental measurements. This method is very important for engineering material characterization. Thermal conductivity insights. Materials such as diamond, silver, and copper have extremely high thermal conductivity. In contrast, air and insulating materials such as glass fiber have very low conductivity. The range of conductivity values is very wide, from metals to insulators. This difference explains why metals are suitable as heat conductors and certain materials are suitable as insulators. This understanding is essential in engineering material selection. Thermal conductivity spectrum. Among all materials, non-metallic crystals such as diamond and graphite occupy the highest positions in thermal conductivity. Metals and their alloys lie in the middle range as good heat conductors. Gases, fibers, and foams are at the lowest level and act as insulators. This spectrum shows that the microstructure of materials strongly influences their heat conduction ability. This classification helps engineers select materials according to their thermal function. Check your understanding number 7. This question tests the understanding of material classification based on thermal conductivity. The correct answer states that non-metallic crystals have the highest values, metals are in the middle, and gases and foams are insulators. This classification matches the conductivity spectrum discussed earlier. This understanding is important to avoid mistakes in material selection for design. It also reinforces the link between material properties and their functions. Thermal conductivity of alloys? Alloys generally have much lower thermal conductivity than their pure metal components. The addition of other elements disturbs the crystal structure and hinders heat flow. Examples such as constantan and bronze show a significant reduction in conductivity. This property is often utilized in applications that require thermal resistance or certain thermal stability. Therefore, alloys are selected not only for mechanical strength, but also for their thermal properties. Mechanisms of heat conduction. In gases and liquids, heat conduction mainly occurs through molecular collisions and diffusion. In solids, the main mechanisms are lattice vibrations and the movement of free electrons. This difference explains why metals are very effective in conducting heat. The internal structure of a material strongly determines how thermal energy is transferred. By understanding these mechanisms, the thermal behavior of materials can be predicted more accurately. Variation in thermal conductivity. In metals, thermal conductivity generally decreases as temperature increases. This can be observed in copper and aluminum, which show reduced conductivity at higher temperatures. This phenomenon is related to increased disturbances in electron movement. It means that thermal properties are not always constant under all conditions. For high-precision analysis, this temperature effect must be taken into account. Thermal conductivity across phases. In the solid, diamond has the highest thermal conductivity, while silver and copper dominate among metals. In the liquid, water shows a relatively stable value compared to other liquids. In the gas, helium has the highest conductivity, and its value increases with temperature. These differences across phases show the strong influence of microscopic structure and mechanisms. This demonstrates that thermal properties strongly depend on the physical state of the material. Check your understanding number 8. This question asks which gas has the highest thermal conductivity. The correct answer is helium, as discussed earlier. This property makes helium useful in applications that require rapid heat transfer. The question reinforces the understanding of thermal property comparisons among gases. By mastering this, working fluid selection can be done more appropriately. Thermal diffusivity insights. Thermal diffusivity indicates how fast heat spreads within a material. Metals, such as silver and gold, have high diffusivity and respond quickly to temperature changes. In contrast, insulating materials like wood and glass wool have low diffusivity, so temperature changes occur slowly. Liquids and organic materials are generally in a similar low range. This property combines the effects of conductivity, density, and specific heat into a single parameter. Thermal conductivity conversion. In the English unit system, thermal conductivity values can be obtained from SI values using a specific conversion factor. The factor 0.5778 is used to convert from watts per meter degree Celsius to BTU per hour foot degree Fahrenheit. A numerical example shows how the same physical value can be expressed in two unit systems. This conversion is important when working with different data sources or standards. Unit consistency strongly determines the correctness of calculation results. Heat transfer via convection. In convection, there is a boundary layer near the surface where velocity and temperature change rapidly. The air temperature drops sharply from the hot surface value to the ambient value. Heat always flows from the hot surface to the cooler fluid. The velocity profile shows how the flow develops away from the surface. This mechanism combines conduction near the wall and advection by the fluid flow. Convection cooling.
Forced convection uses devices such as fans or pumps to increase the fluid flow rate. Natural convection occurs due to density differences caused by temperature variations. Under the same conditions, forced convection is usually much more effective in removing heat. This is because higher flow rates reduce thermal resistance. The choice of convection mode strongly affects cooling system design.
Check your understanding. Number 9. This question compares the fundamental difference between forced and natural convection. The correct answer states that forced convection uses external forces, while natural convection relies on density differences. This difference determines the flow velocity and the effectiveness of heat transfer. This understanding is important when selecting an appropriate cooling method. With this concept, design solutions can be made more rational.
Sir Isaac Newton. Newton made major contributions to classical mechanics and also to heat transfer through the law of cooling. Newton's law of cooling relates the convection heat transfer rate to the temperature difference. This concept is still used today in many convection correlations. In addition, his work in mathematics and physics forms the foundation of modern engineering science. His role shows how one scientist can influence many disciplines at once. Convection heat transfer coefficients have a very wide range of values, depending on the mechanism and the type of fluid. Free convection in gases has small values, while in liquids the values are larger. Forced convection significantly increases the coefficient values. Boiling and condensation produce extremely high values because they involve phase change. This range shows how varied convection intensity can be in practice. Black body radiation. Black body radiation represents the maximum possible emission from a surface at a given temperature. An ideal black body has an emissivity equal to 1. The radiation rate strongly depends on temperature and increases with the fourth power of the absolute temperature. This concept serves as a reference for comparing the radiation behavior of real surfaces. With this model, radiation analysis can be carried out systematically. Emissivity of materials. Emissivity indicates how closely a surface behaves like a black body. Polished metals have very low emissivity and reflect most of the radiation. In contrast, black paint, human skin, and water have high emissivity. Many non-metallic materials fall in the medium to high range. This value is very important in radiation heat transfer calculations. Check your understanding number 10. This question asks about the typical emissivity range of polished metals. The correct answer is about 0.02 to 0.03. This very low value explains why shiny surfaces are effective radiation reflectors. This concept is often used in the design of thermal shields and radiation insulation. Understanding these numbers helps in estimating radiative heat losses. Radiation absorption and reflection. When radiation strikes a surface, part of the energy is absorbed and the rest is reflected. The fraction that is absorbed is determined by a material property called absorptivity. The higher the absorptivity, the smaller the fraction of energy that is reflected. A simple balance between incident, absorbed, and reflected radiation is very important in thermal analysis. This concept is the basis for understanding radiation interaction with real surfaces. Radiation heat exchange. A surface always emits radiation according to its temperature and emissivity. At the same time, the surface also receives radiation from its surroundings. The net radiative heat transfer is determined by the difference between the emitted and the received energy. Therefore, the surrounding temperature strongly affects the radiative heat transfer rate. This concept is important in the analysis of high-temperature systems. Heat transfer mechanisms.
In solids, conduction is the primary mechanism of heat transfer. In gases, heat transfer can occur through a combination of conduction, convection, and radiation. In a vacuum, the only possible mechanism is radiation. This shows that the medium strongly determines how thermal energy is transferred. This understanding is important for analyzing systems under different environmental conditions.
Check your understanding number 11. This question emphasizes that without a medium, conduction and convection cannot occur. The correct answer is radiation as the only heat transfer mechanism in a vacuum. This concept is very important in the analysis of heat transfer in outer space. Without this understanding, the analysis of satellites and spacecraft would not be accurate. It also highlights the unique nature of radiation compared to other mechanisms.
Heat transfer reduction methods. Various methods can be used to reduce the rate of heat transfer through a wall. An air gap provides moderate reduction by limiting conduction and convection. A vacuum eliminates convection and leaves radiation as the main mechanism. Superinsulation combines vacuum and special materials to achieve very high thermal resistance. This comparison shows how insulation design can be optimized.
Exceptional insulation with silica aerogel. Silica aerogel shows exceptional insulating capability despite its very low mass. This material can protect objects from extremely high heat, such as direct flame. Its structure, which consists mostly of air, makes conduction and convection very small. This makes it suitable for extreme applications with space and weight limitations. This example shows how material engineering can produce extraordinary thermal properties. Aerogel nanostructure. Aerogel has a porous structure with nanoscale pore sizes. The network of interconnected particles creates an extremely large surface area. This structure results in very high resistance to heat transfer. At the same time, its density remains very low, making the material extremely light. The link between microstructure and macroscopic properties is very clear in this material. Check your understanding number 12. This question compares the effectiveness of different heat insulation methods. The correct answer states that an air gap reduces conduction and convection, while superinsulation combines vacuum and advanced materials. This sequence shows a progressively greater reduction in heat transfer. This understanding helps in selecting the most appropriate insulation solution. It also emphasizes the role of system design in controlling energy losses. Problem solving using PTD concepts. The problem-solving approach starts by identifying important variables and relevant physical properties. Then, reasonable assumptions are made to simplify the system without losing its physical essence. Heat and mass transfer equations are derived based on these assumptions. The obtained solution must be consistent with the prevention through design principles and physical constraints. This approach ensures that the solution is not only mathematically correct, but also engineering-wise reasonable. Simplifying problem solving. Complex problems should be broken down into smaller and more manageable steps. A logical and structured approach usually leads to faster solutions with fewer mistakes. Avoiding unnecessary complexity saves time and effort. This strategy also helps maintain focus on the main objective of the calculation. In this way, the problem-solving process becomes more efficient and more reliable. Importance of reasonable assumptions. Identifying missing data is an important step before performing calculations. The assumptions made must balance simplification and accuracy of the results. Incorrect assumptions can lead to significant errors in the final outcome. Therefore, every assumption must be physically justifiable. This approach increases the reliability and credibility of the analysis results. Ensuring result accuracy. Calculation results must be checked for physical and economic reasonableness. Rechecking data, assumptions, and calculation steps is essential to avoid errors. Extremely unrealistic values often indicate conceptual or computational mistakes. Evaluating the plausibility of the results helps ensure that the solution can be applied in practice. This step is an important part of engineering ethics and professionalism.
Check your understanding number 13. This question emphasizes the importance of reviewing calculations and assumptions. The correct answer is to identify errors or oversights in the data. This step often saves engineers before results are used in technical decisions. Without this process, small mistakes can grow into major problems. This question reminds the importance of being critical toward one's own results.
Accuracy versus precision. Accuracy indicates how close a result is to the true value. Precision indicates how consistent repeated measurements are with each other. A result can be very precise but not accurate, or accurate but not precise. The shooter example illustrates the conceptual difference between these two terms very clearly. In engineering, both are important, but they have different meanings.
Understanding significant digits. Significant digits indicate the level of precision of a numerical value. They start from the first non-zero digit and reflect the quality of measurement data. Scientific notation is often used to clearly show the number of significant digits. Writing 4.03 times 10 to the fourth is more informative than writing 40300 directly. This concept is important to avoid giving a false sense of accuracy in calculations.
Importance of significant digits. Calculated results should not have higher precision than the input data. Rounding must be performed so that the number of significant digits matches the original data. Showing too many digits can mislead the interpretation of results. This principle keeps reported results scientifically honest. In this way, the quality of data and calculations is maintained.
Check your understanding number 14. This question emphasizes the best practice in reporting calculated results. The correct answer is that results should match the number of significant digits of the input data. This prevents making unrealistic claims about precision. This principle is very important in scientific and engineering reporting. By following this rule, the communication of results becomes more reliable.
References. The reference list shows the main sources used for the lecture material. The book by Chingle and Gajar is one of the standard references in the field of heat transfer. This reference ensures that the presented material has a strong scientific foundation. Using credible sources is very important in engineering education. It also makes it easier for students to study the material further on their own.